Let's get started on the last unit of this course. I can't believe we're there. This is a very fun topic to teach. There's endless opportunities to do things with differential equations. So we're just barely touching the tip of the iceberg in this course, but I hope it will set you up for a lifelong of curiosity and learning, because differential equations are the cream of the top of the cherry of the icing of the cake of scientific accomplishments. There's nothing better in modeling than differential equations. And differential equations have done me a lot of good in my career, as opposed to data science, but we'll get a chance to discuss that. But there's not a single data science model now that can beat the physics brought in by differential equations, okay? And I hope in this unit that I will get to revisit differential equations with you, at least at the ordinary differential equations level. So who is currently taking ODEs and who has taken ODEs? Okay. Okay. So for those of you who didn't raise their hands, have you never had an ODE class? Okay. Okay, do you plan on like taking one next year? Yeah? Okay. Oh, you did. Okay. So I guess you've all seen ODEs or are currently taking it. Okay, that's great. Because I hope to give you a different perspective. You probably learned it from the math people who are going to be more focused on like things like existence of solutions and analytical solutions. In this unit, I'm going to give you a different perspective on differential equations. And in fact, we're going to build, depending on time, or you are going to build, or we might build together a model for the pandemic. Now, that was very exciting during the early days of COVID, and everybody didn't know what was going on. So we built this model together here in class, and different students started coming up with their own different models to track like social distancing, masking, hospitalizations, etc. It was quite interesting in seeing kind of the effects of. We discovered that there was like a threshold point where shutdowns become ineffective, right? Where you're like shutting down everything, then we try to add cost to that. Anyway, that's the stuff you could do with differential equations, okay? However, before we get there, we need to start with something called numerical differentiation. So that will revisit a topic we touched upon earlier when we did the heat transfer problem. It's just one lecture, but I need that discussion so that we have all the tools that we need to do differential equations, okay? So when you think about it now in this course, the first unit was solving algebraic equations, right? The second unit was curve fitting or data analysis. Now the third unit is solving differential equations, okay? Why did I put differential equations at the end? Because they're a little harder. Working together through regression and interpolation kind of made us better fit to do Python stuff and reuse linear solvers and nonlinear solvers. We're going to need all of that with differential equations. But first, because there was no life hack today, I'm going to give you this life hack, okay? The life hack is not to tie your horse with a chair, if you have a horse, but the life hack is that sometimes the thing that is holding you back is all in your head, okay? So from the horse's perspective, the horse is tied up, right? But it doesn't know it's tied up to a chair. It could easily just yank that chair and just keep moving, right? So put things in perspective. You know, take a larger perspective sometimes, okay? And you realize that, oh, you know, this is just all in my head, and I could perhaps get over this obstacle or hurdle. All right, numerical differentiation, and I don't know, this is the wrong semester clearly, so this is spring 2023. Okay, spring 2023. At the end of this chapter, you should be able to do the following. Define the finite difference method. We kind of know what it is a little bit. Numerically compute the first and second derivatives for discrete data and continuous functions. define and estimate the convergence rate of finite difference schemes, finally, define what is meant by order of accuracy of a given finite difference scheme, and then use the Taylor series to derive a few simple finite difference schemes. If you remember the heat transfer problem, I told you one day I will show you how we can convert that second derivative to ti plus 1 minus 2ti plus ti minus 1 over delta x squared. We're getting there. This is the step that gets us closer to that. Now, we did touch upon a little bit on the finite difference method when we did the forward difference method early when we were computing errors, right, and the truncation error, right? So we did the Taylor series and we truncated it. So we're going to revisit that and build upon that a little bit more. The motivating question, and that also comes from COVID, probably I have to replace this problem next year because this is not an issue anymore, but this plot was like early into the pandemic. This was taken in 2020. I was teaching this course, and then, you know, we reached, this is like days since the outbreak, day 0, okay, day 40. So this was like a month and almost 5 weeks into the pandemic. I showed this plot, and then the next lecture we had to go online, okay? And so this is showing the data for mainland China in blue, all right? And then, you know, as it spread out from mainland China, then the world started picking up infections in orange, right? So we have these two sets of data, total number of cases, okay, for both mainland China and the world. And then the question is, what is the rate of spread of COVID-19? How fast is it spreading worldwide, given these data? So what would you do? I gave you this data. Yeah.
My initial thought would be to calculate the rise over run for each data
Okay.
and then take the average.
Okay. Yeah, calculate the derivative. And take the average of what?
Of each rise over run, like for like an average rate of change.
Or you can just do it at each point. It just gives you one value, right? And because you need it daily, right? So at the end, what we're really interested in is really at the end, like what is the rise over run? So you would do it at each point, right? You don't have to take the average over the full data set, okay? Yeah, what other ideas? Todd?
You could do something like for the first part of the population model where everybody gets like it's first exponential and then it gets to
Okay.
capacity, and you could do a different model for the orange data once it gets spread to the other part of the world.
Okay. Okay, yeah, so what Todd is saying is we can fit something. We can fit a curve, whether in turbulent or like a regression, do a regression curve by building maybe early on an exponential rise, and then, you know, when we hit a plateau, which you call carrying capacity, perhaps that's more to population growth, but we're going to visit that in a few slides, well, in the next lecture. But yeah, so you would fit a model and then differentiate that model and then evaluate the derivatives, right? We're going to do the former idea. We're going to do the idea that Ethan suggested for numerical differentiation. Why? Because I need numerical differentiation to build up for differential equations, okay? So yeah, those are the two ideas primarily. We're going to use a Taylor series over here to define these derivatives. Now, the rise over run gives you the derivative locally at a point. And yeah, we all know that. But that's only one way to compute the derivatives. There are other ways that have less error in them that allow us to compute derivatives and give us better approximations. Now, the other question is, what if you wanted to calculate the second derivative, right? So it's not rise over run. You'd have to do some more algebra to figure that out, right? So we're going to use the Taylor series to build up these approximations to the derivatives. Now, remember this slide from the Taylor series. That was like early on when we talked about the error. We already defined what the Taylor series is, but a quick reminder, for any continuous function or any function that exists that gives you data, you can express that function at any point x, at an arbitrary point x, around any other point. We call it x naught over here. And this would be the formula. So the idea is that if you know everything at some other point, okay, then you can express at some point x0, you can express the function at any other point using this Taylor series. Okay? So now we're going to use that to try to compute derivatives of discrete data or continuous functions. All right? Here's the situation. Here's the setup. You have a bunch of data points discretely organized over what I'm going to call a grid over here. So on the x-axis, you have these points x1, x2, all the way to some point xi, all the way to xn endpoints. And the spacing between these points for now is fixed. The spacing is h. Okay, it's a fixed value, constant everywhere. And for each one of those points, there's a function value, f of x1, f of x2, and so on. Okay? And there's a curve that passes through all of those points. All right? So for simplicity now, I'm going to call f of xi, I'm going to call it fi. So I don't have to carry a bunch of parentheses that are annoying. So when I say fi plus 1, it means f evaluated at xi plus 1. Okay? Okay. Now I'm going to compress those over here so we can simplify what we're looking at. All you need to know is that for these coordinates, okay, or for these independent variables below x1 all the way to xn, you have a bunch of function values f1, f2, all the way to fn. Okay? Now, given these function values, the Taylor series is useful in finding the derivatives of that function, right? So in other words, your objective is to find f prime at xi for any I. So our objective is to find the slope of this function f at an arbitrary point xi. Okay? All right. Now recall the Taylor series before you do the activity. Recall the Taylor series is the Taylor series of the function f at some point x is equal the function value at some point x naught, its derivative at x naught times x minus x naught, and so on. Now I want you to write the Taylor series of f at xi plus 1 around xi. Okay? So f at xi plus 1 around xi. So your x naught is going to be xi. So go ahead and just write this down as is, first term, second term. Okay? But do it for f of xi plus 1 around point xi. This is the Taylor series of f of x around x naught. Okay? Just simple substitution. Don't lose our objective. Our objective is to get to compute f prime at xi, okay? But this is the trick to get to it. Is we first write the Taylor series of f at xi plus 1 around f of xi, okay? And see what happens. Okay? You guys have it? Yeah? Okay, what did you do? What did you do? You just replaced?
X with xi plus 1.
Uh-huh.
X naught xi.
Uh-huh. Same thing here. And what about this guy? You get?
I guess you get like delta x.
Or h, right? So you get xi plus 1 minus xi, which is h, right? Okay, that's right. So very simply, all you have to do is set x to be equal to xi plus 1 and x naught to be equal to xi. These are just dummy variables, okay? But when you connect them to I plus 1 and I, that gives you an anchor point that we're expressing the function f at this point using the previous point, at point xi plus 1, using information at point xi, okay? So you simply substitute x with xi plus 1 and x0 with xi. You get this. And now remember, our spacing is fixed. So xi plus 1 minus xi is equal to h. And then you simplify the nomenclature of f of xi plus 1 is fi plus 1 and fi. And you get this nice compact formula. Fi plus 1 is equal fi plus h fi prime, etc., and so on. Okay? Now this is cool because now we were able to relate we have the function values, all of the f's everywhere, okay? That's given to us, all right? Suppose it's given to us, okay? And now we have a relation between the point at I plus 1 and the point and the value at I, but we also have a bunch of unknowns, actually, f prime I, f double prime I, and so on, okay? So now do what we did also during the errors lecture. Solve for f prime I. So move f prime I to the left-hand side and move everything else to the right, and give me a formula for f prime I, okay? Don't be afraid to put 3 dots, okay, etc., essentially saying. Yeah. So we did this also, if you remember, early on in the error analysis chapter. And I promised you we'll come back to it, but we're going to dig a little bit deeper this time. If you solve for f prime I, so treat f prime I as your unknown. Okay, so move it to the left-hand side, divide by h, move everything to the right-hand side, divide by h. Did you get, Todd? You get something? What do you have?
Oh, you want to tell me?
Do you want to tell me?
F prime I equals
Parentheses. Uh-huh.
fi plus 1/2 h squared double prime I.
Okay.
Dot, dot, dot.
Over h. Okay, that's right. You just simply solve for f prime. You just take f prime to the left-hand side and express it in terms of everything else. The way I like to write it is divide by h. Divide every term by h. Okay. So you get fi plus 1 over h minus fi over h. I'll combine them into this, and then the rest. You know, h squared, we had h squared f double prime divided by h becomes h f double prime, right? And the same thing for all the subsequent terms, okay? Now, this term reminds you of something. Yeah?
Would it not be minus 1/2 h double prime I?
No, because, yeah, sure. It doesn't matter, actually. It doesn't matter, but you're right. I actually cannot edit this equation right now, but you're right. Yes. Okay, there's a sign issue here. This should be a minus. Thank you for pointing that out. Okay, but it's not going to matter because that's going to be a truncation error. Okay, we're going to call it order h. Yeah, we're just going to, we don't care about the sign for it. Okay, but it is important as you're building higher order approximation. We'll see. Okay, now this first term reminds you of what you learned in high school. Rise over run. Okay, fi plus 1 minus fi over xi plus 1 minus xi, right? And that's indeed the definition of the derivative. Okay, now in the limit as h approaches 0, all of these terms disappear and you get the exact derivative, okay? But we're not going to do this limit because we are doing discrete mathematics. And then we can define an f prime, a way to compute f prime given only fi's by neglecting all of those terms that we don't know. We don't know f double prime, we don't know f triple prime, we don't know any of those. So why not just neglect them? And you could argue that, well, all of those derivatives are multiplied by h squared, h cubed, and as h gets smaller, those derivatives are bounded, so they don't go to infinity. As h gets smaller, all of those terms are going to go to 0, okay? So in that case, then we can justify neglecting those terms, and then we say our approximation to the derivative, see the approximate sign, is fi plus 1 is fi over h, right? That's one way of doing it, with the error being all of the other terms. And remember, we called that the truncation error. It's taking an exact mathematical expression and chopping it, removing some pieces of it. Those pieces are called the truncation error. Now, for this method, so now what we accomplished here is given only function values, fi plus 1, fi minus 1, etc., we can compute the derivative at any point. Okay, just given the function value, we can approximate the derivative. No mystery, no magic here. The new stuff you're going to learn is about the truncation error. Now, the truncation error, again, if you go back to our definition in error analysis, is typically dominated, is always dominated by that leading order term. Okay? Because the way to think about this is that we're going to keep h, which term is smaller compared to all the other terms? as h gets smaller, this term is going to dominate. This leading term is going to dominate. So we say that the error on average behaves proportional to the leading order term, okay? Now, in this case, f double prime for a given problem, in all cases, these second and third derivatives, they're bounded, okay? If you're dealing with a physical problem, they're not going to go to infinity, right? They're bounded by a value. And that value is independent of h, of the spacing. So really, that value is a constant, okay? That value is a constant. So we say that the error is proportional to h, the spacing. Now, h, the sensitivity to h, is very important here, because that's the only parameter we can control when we are building an approximation to a function. You can use double the spacing, or you can triple the spacing, right? So what happens to the error as you change your spacing? That's why I like to express things in terms, you asked me a question, I think last week, for the integration. Why do I like to express it in terms of n? Because that number of that number of segments for the integral is what I can control. So I want to express the error in terms of that. And same here, we want to express the error in terms of the spacing h. So our truncation error is always bounded by some constant times h in this case. And then we call this order h. Now this notation, big O notation, order h, all that means is that the error scales with h. Or order h means that my error, or whatever, if you say something is order h, it means it's, yes?
What is the
Big O, that's what I'm defining right now.
Just like, no, like what the
It's order, order. That's what it says. It's order h. Big O means order. Pardon me?
I said, how do you type it in LaTeX?
Oh, this one? MathCal, backslash MathCal, math calligraphy, so backslash MathCal, okay? But this symbol means order, and it's called the big O notation. What it means is that when I tell you something is order 10, when I say something is order 10, it means it's not 0.1, it's not 0.5, it's not 100, it's not 1,000, it's 15, 12, 23, 18, that's, okay? Order h, it means something is just proportional to h. It's not proportional to h squared, it's not proportional to h cubed, it's proportional to h, okay? And that has a very, very specific meaning, okay? So then you could say exactly now, we could write the approximation to the derivative, f prime at I is equal f at I plus 1 minus f at I over h plus order h. And look at the exact, this is exact notation, okay? Because all of those terms are, we just say they're order h. They, however you change things, they're only going to scale with h. They're only going to change with h, okay? Now visually, if this is the true slope, the forward difference approximation gives you the following slope, okay? Now this is bad for this example, but I could come up with an example where the forward difference is better than any other difference, okay? But this is visually what the forward difference slope gives you. The exact true slope is the line tangent to that point at I. The forward difference is going to give you that slope over there, okay? All right, so now let's go back to this error. This is important, okay? We say that the error is order h. This means that the dominant term in the truncation error is proportional to the spacing h. Now here's the kicker. This also means that if h is cut in half, the error will also be cut in half. If you remember that first or second homework, I asked you to compute the derivative using the forward difference approximation for values of h like 10 and then 5 and then 2.5. You cut it in half. And I asked you, what do you observe? What does the error, how does the error behave? Okay? And then the answer was, that method was order h. So as you cut h in half, the error is cut in half, okay? So let's prove this. If the error at some spacing h is equal to ch, then if you cut the spacing in half, then the error at h over 2 is c times h over 2, but ch is eh. So the error when h is cut in half is equal to the original error cut by 2. So you cut the error, if you cut h in half, you cut the error in half. Okay? I see some squints. For some spacing h, you have some error. If you cut h in half, what happens to that error? It gets divided by 2. Yeah? O is in a way a blanket nomenclature for the entire truncation error. O is not a value. It's not a value. It's not a value. I mean, you can express the entire truncation error, but O of h says that all of that term that is represented by O of h, order h, is dominated by h. And it behaves, it changes in a way that's proportional to h.
So it's kind of just there to show the rest of it.
Yeah, to hide all of that into one term, because I'm not going to carry that truncation error and the 3 dots everywhere. We're just going to call it OH, but then we know that the behavior of that term, all of those, there's an infinite number of terms there. All of those terms are going to be dominated by a constant times h. That's how the trend is going to be. Okay, and we're going to prove this when we jump on Python. Yeah. But yeah, as the bound, as the upper bound of the error. Yeah, as the upper bound for the error. Okay, so what you should take from this is the meaning that when you have a method that's order h, what it means for the error. You immediately could say a method of order h means that the error is a constant times h. Okay? All right. Now, in general, an approximation is said to be of order p if the truncation error is order h to the power p. Okay? So remember, our truncation error had h, f double prime, etc. For this case, we're going to develop methods where the truncation error is, the first term in the truncation error is h to the 4th. So that method is a 4th order method, and the truncation error is ch to the power 4, or order h to the power 4. Okay? Now, show that if a method is order h squared, then if h is cut in half, the error will be cut by a factor of 4. Okay? So write EH equals CH squared and deduce what happens to EH over 2 in terms of EH. What happens to the error? You're starting with an error at some spacing. You cut the spacing in half. What happens to that error? Just write it down. Because then it gets interesting when you have like cubics and other things. So write EH equals CH to the CH squared, and then write EH over 2.
So in the case where we have an order of age, then the relationship between how we change age and how much more accuracy we get is going to be a linear relationship.
Yes, you got it. You got it. You got it. Then if you have a higher order method, a second order method, then doubling your resolution is going to get you a way fast, way more accurate results. Okay? So the relation between the spacing and the error is going to be second order. So, yeah.
How do we find this? Are we integrating it? Because it's
No, we're just looking at the error. What happens to the error, the truncation error, if you have a method whose truncation error is CH squared?
No, I just mean like later, like with the whole this way integrating this.
Yeah, so we're gonna we're gonna use it in different ways. In this chapter, we're just gonna use it to calculate derivatives, but in the next chapter, we're gonna use it to convert a differential equation to a system of linear equations. Okay. All right. So if EH is CH squared, then EH over 2 is CH over 2 squared, which is CH squared over 4, but CH squared is EH, so you've cut your error by a factor of 4. Okay? Just by doubling your resolution, you've cut your error by a factor of 4. If you had a method that was first order, or order h, okay, you cut your resolution in half, or you double your resolution, then you only cut the error by half. So that justifies using higher order methods. Okay? A higher order method, such as one that is second order, there are third order, fourth order, fifth or 10th order methods all the way through. Okay? Okay. Now that's important because it's going to help us assess our finite differences. One last thing before you go. If you take the log of the error, log E equal log C plus P log H, and then you plot that, I'm going to ask you this activity. If you plot that on a log-log plot, so log E versus log H, then that is a straight line, right? Because that is equal y equal A naught plus PA1, okay? And this is what you get. And the slope of that line is the order. So a first order method on a log-log plot, if you plot the error versus the spacing on a log-log plot, you're going to see a straight line with a slope of 1. If you plot a second order method, the error in a second order method versus spacing, you're going to get a line with a slope of 2. Okay? We'll continue on Tuesday. We'll revisit this, and good luck studying over the weekend. Okay?